Hello everyone. In this video, we're going to be talking about finding area under a curve. And you might be wondering, what does this have to do with what we talked about in the previous video, which was antiderivatives? And the answer to that question is, you'll see. But for now, this is going to seem pretty unrelated. Well, what do I mean by area under a curve? So let's say we're given some function f of x. What we're going to be doing today is looking at how can we find the area under a function between two specific x values. And notice by when I say under a function, we're bounded by the x-axis. We're stopping at the x-axis. So it's really, when I say area under the curve, we're really talking about the area between the function and the x-axis. Now you may be wondering, why would this be useful to know? Well, consider this situation. Let's say I'm out driving on I-15 and I'm driving 80 miles an hour for 3 hours. My question then becomes, how far did I travel in total? What was the total amount of distance I traveled? Well, some of you guys may automatically recognize that, oh, this is just multiplication. I can just do 80 times 3. And the reason why is because 80 miles per hour is really just that proportion or that rate of 80 miles per 1 hour. And if I multiply it by 3 hours, I get that total distance, 240 miles. If I were to graph this, I could let my y-axis represent my velocity or my speed. And my x-axis could be time. Well, what do I know about my velocity or speed? I'm traveling at a consistent 80 miles per hour, which means this ends up just being the constant function of 80. I end up just having this horizontal line here at 80 miles an hour. And how long does this last? This lasts from the time I start my drive for 3 hours. Well, notice if I were to find the area under this function over this 3 hours, what shape does that make? It ends up just making a rectangle. What's the height of this rectangle? Well, I can see that over on the left side. It's just that distance of 80 because I'm going from 0 at the bottom all the way to where my line is, which is at 80. Well, what's the width of my rectangle? Well, that's going from 0 to 3. So that length is just 3. So my area is just 80 times 3, which is 240. It turns out that the area under this curve tells me the total distance I actually traveled. So area under the curve can be meaningful. In fact, given any rate function, notice in this example, my rate function was my velocity, right? My function measured with the velocity that I was traveling. Given any rate function, the area under the curve, or the area between the curve and the x-axis, this is just more convenient to write, represents the total change over that specific interval that you're looking at. So area under the curve becomes really, really useful once I think about it in that way. So it then leads to the question of, okay, how do I calculate area under the curve? Well, in this example, is really simple. Why? Because the area that I was trying to calculate was a nice geometric shape. And that's actually true for any linear function. If the function is linear, then I can calculate the area under the curve using just geometry. I can break up my shape into rectangles and triangles and calculate the area of each of those rectangles and triangles. So that's something that we'll go through. I'll go through an example of that in an examples video, but I'd love for you to try one out just on your own first to see if you can figure out how to do that, and then you can watch that example video if you're still a little confused about that. Well, what if the function's not linear? What if it's something like this, where it's got a curve to it? If it's got a curve to it, the area it creates doesn't match any geometric shape that we know about. At least in most cases, it won't match. So how do I find this area? Well, right now, all we can do is just estimate. So that's what we're going to do, is we're going to just estimate the area in these cases. We're going to estimate the area under the curve. And we're going to do that by using something called a Riemann sum. So what is a Riemann sum? Let's talk about it. So let's look at that example. I've got my curvy function, and I'm evaluating the area under the curve from the x value a to the x value b. Well, the easiest way for me to estimate this area is just by forgetting about the curvy parts and just making it a rectangle. That means picking some frame of reference, picking some y value along this line. I'm going to just start with this very first y value and just drawing a horizontal line from there. That makes a nice simple rectangle that, as we've already talked about, I know how to find the area of a rectangle. That's nice and simple. So let's do that. Let's find the area of this rectangle. Well, the area of this rectangle is just height times width. So what's the height of this rectangle? Well, since I'm starting at the x-axis represents 0, the height is just however high I have to go for this y value. How do I find this y value? I can use the function by just plugging in my starting x value, a. So the height of this rectangle is just f of a. Another way I can write that is x sub 0. X sub 0 represents your starting x value for your interval. So that's the height of the rectangle. What about the width of the rectangle? The width is just this distance from your starting x value to your ending x value, and I can find that using subtraction. That's just b minus a. And that would be my estimation. But this really isn't the most accurate estimation. There's a lot of area that we're not counting by estimating it this way. So is there a way I can make this more accurate? Well, some of you guys might be thinking, oh, just use a different point. Maybe if I use the midpoint of the interval as my reference point and build a rectangle from there, that could be more accurate. Or what if you made like a triangle or a trapezoid to do the area? And yes, in this case, that probably would be more accurate. But whether or not these methods actually end up being more accurate really depends on the shape of your graph. If my graph were shaped a different way, then using the midpoint may not be more accurate, or making a trapezoid may not be more accurate. So instead, let's think about a way to make it more accurate that works for any function. Well, it turns out that another way I can make it more accurate is simply by making more rectangles. What do I mean by that? Instead of only picking one y value and going straight across, what if I picked two y values? And instead of only making one rectangle, I made two rectangles. Because I'm using more data points, this has a very high likelihood of making this more accurate. And in fact, I could keep going. What if instead of doing two rectangles, I did four rectangles? Meaning, what if I used four y values as reference points? The smaller the rectangles and the more I make, the more accurate this estimation becomes. It does mean more calculation though. So let's think about how the calculation changes if I add more rectangles. Let's focus on the first rectangle. It's still a rectangle, meaning I still find the area in the same way. Height multiplied by width. What's my height? Well, the height is still a y value that depends on that starting x value. So that still represents my height for my first rectangle. But now, what's the width of this rectangle? The width has changed, because instead of being the entire width of the interval, I've now split it up into, in this case, 4 pieces. So I can just divide that total width into as many pieces as I need to. So I'm writing b minus a over n because n is going to represent the number of rectangles that we're using. So in our case, since I'm using 4 rectangles, I would divide by 4. We actually have a mathematical term for this. This is considered my delta x, or my change in x. And it follows that formula, b minus a over n. But that only takes care of this first rectangle. I still need the areas of each of the other rectangles. So if I move on to the second rectangle, how is it different? It still has the same width. The width is still the same, but I'm now using a different x value to reference. I could consider this x sub 1. It's my first new x value that I'm now going to reference to figure out the height of the rectangle. The height, of course, is still a y value, so I do have to plug that value into my function. But there's the area of my second rectangle. For my third rectangle, I'd use a new x value. And then for my fourth rectangle, I'd use another x value. So for each of my new rectangles, I'm using a different x value as my reference point to figure out the height of that rectangle. Remember, that's what's making it more accurate, is because I'm using more reference points. But once I find all of the areas of these rectangles, what do I do with them? Well, because I want to estimate the total area, I'm just going to add these together. And that's where this idea of a Riemann sum comes from. That's where this name comes from, is because we're summing up the areas of all of these separate rectangles. So, if I were to mathematically define what a Riemann sum is, it's this summation. That's what this fancy E symbol means, is it's a summation symbol, meaning you're going to be adding a bunch of things up. It's the summation of all of my different areas. And how do I calculate areas? I find the height by finding the function value at some specific x value. That's what x sub I is going to represent. Multiplied by whatever that width of my rectangle is, whatever delta x is, because that represents the width. And that, of course, depends on how many times I split it up. And the last part of a Riemann sum is how many of these things are we actually adding together? Each of these represents the area of one rectangle. How many rectangles am I going to have? I'm going to have n rectangles. And so to show how far I do this, I'm going to put a little n above this notation to show, hey, that's where I'm going to stop. That's how many of these I'm going to do. And then if I have an ending point, I also need a starting point. And so this right here at the bottom tells me I'm going to start. So this is my formula for Riemann sum, but I do have to be careful because there are actually lots of different types of Riemann sums. And this notation that I've used is for one specifically. Well, in this section, we're only going to be talking about two different types. We're going to be talking about a left-hand Riemann sum and a right-hand Riemann sum. If I go back to my graph, maybe you can already tell what type of Riemann sum would my graph represent. This actually represents a left-hand Riemann sum. Why? Because for each rectangle, I'm using the left x value, the left side of the rectangle, as my reference point to show how high it goes. Right? And that's true for the second rectangle too. If I look at that second rectangle, I'm using the left side x value, the x value on the left side, to judge how high to go. So this is considered a left-hand Riemann sum, because I'm using my left endpoints as my reference points. Now I could easily change that and use my right-hand endpoints for each of my rectangles. So if I were to redo this as a right-hand Riemann sum, for this first rectangle, instead of looking at x sub 0, I would look at x sub 1. I'd follow x sub 1 up to the top where it hits the function, and that's what I would choose as my height for my rectangle. And that would be a right-hand sum. So the only difference between these two things is just which x value, which side of your rectangle are you going to have go up and hit the function? Which x value you're going to use as your reference point. So this is what a Riemann sum is, and you're going to have a few chances to use this idea of estimating area under the curve using a Riemann sum. Well, with this example, we started by just looking at estimating using one rectangle. Then we looked at two rectangles. Now we have four rectangles. What's stopping me from keeping going? If I have a continuous function, I can pick an infinite number of x values to use as my reference points, and therefore, I can theoretically have an infinite number of rectangles. And so by doing this, I can actually find the exact area under a curve. And we actually have a notation for this. The Riemann sum represents my estimate, but if I let n approach infinity, then I can get that exact area. And what do we use for this notation? We use a skinny s. Wait a second, we've seen this notation before. This is the same notation we used in 4.1 for antiderivatives. The only difference here is I'm going to put bounds on this skinny s. And those bounds are your interval that you're looking at from A to B. But I want to point out how this matches the Riemann sum. We have f of x to represent the height of each of my rectangles, and we have dx to match this delta x. But the difference here is dx is an infinitely small width. So if you see this notation, what it's asking for is the exact area under a curve from A to B. Okay, that takes care of the concept for 4.2. Go ahead and get started on the homework, see what you can do, and then there's a couple of questions that I'll be going over in the examples video. Good luck, and see you in the next one.